All right, here we go. This was the homework assignment that I gave you guys on Tuesday. And this is all about finding the Taylor polynomial centered at whatever they give you for A. So let's go ahead. I'm going to start with problem number 6. So let's do this. All right. So here we go, number 6. So first of all, we have the function cosine of x. And they are asking, oh, sorry, let me do this really quickly, make it a little bit smaller so we can see. So n is equal to 4. So there we go. So what this is going to look like, we're basically saying that f of x is approximately equal to t sub 4 of x, which t sub 4 of x is going to be f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial, which is just 2 times x minus a squared, plus f triple prime of a over 3 factorial times x minus a cubed. And I'll say plus the 4th derivative of f evaluated at a over 4 factorial times x minus a to the 4th. Again, this right here is, the n value, which is what degree they want me to go to. So it's another way that we can say this is find the 4th degree Taylor polynomial. So that's what I got going on, 4th degree Taylor polynomial. So A is this, 2 pi over 3. So really what this is going to be is, so t sub 4 of x is, so cosine of 2 pi over 3. Help me out with that. What is cosine of 2 pi over 3?
-1/2.
-1/2. Boom. -1/2. Plus. So now we're going to have to do a bunch of these derivatives, right? So on, to the side, which actually I'll go down here a little bit and then I'll come back up to it. So I'm going to talk a little bit about the derivatives. So I have, obviously f of x was cosine of x. F prime of x is negative sine of x. F double prime of x is negative cosine of x. The 3rd derivative of f of x is positive sine of x. And then the 4th derivative of f of x is back to cosine of x, right? And so at x equals 2 pi over 3, we just found that this was -1/2. So what's negative? So sine of 2 pi over 3, well, the sine of 2 pi over 3 is going to be what?
√3/2.
Right, so it's going to be negative that, so negative √3/2. Is that Arian talking?
Yeah.
Atta boy, Arian. So then f double prime of x is negative, so that's just going to be +1/2. This is going to be positive √3/2. And then this is going to be back to -1/2. So all of these guys right here, which I'll highlight, all of these guys are the derivatives of the function evaluated at a. So those represent the numerators of the coefficients of the terms in the Taylor series. So going back up to this. Okay. Going back up to this, I now have that f prime of x, when x is 2 pi over 3, is negative root 3 over 2. So this is plus negative root 3 over 2 times x minus a, but a is just 2 pi over 3. Plus f double prime of a, remember what we just got there, that was positive 1/2, divided by 2. So can I just do 1/4 there? Positive 1/2 divided by 2, which is 1/4, times x minus 2 pi over 3 squared, plus f triple prime is of f at x equals 2 pi over 3 is root 3 over 2. But this says divided by 3 factorial. 3 factorial is 6. So root 3 over 2 over 6. Sorry. Yeah, root 3 over 2 over 6 is root 3 over 12. Times x minus 2 pi over 3 cubed plus, now I look at the fourth derivative. Well, the fourth derivative is just negative 1/2, but that's divided by 4 factorial. Well, 4 factorial is going to be 12, right? 4 times 3 times 2, so it's 12. So negative 1/2 divided by 12 is negative 1 over 24 x minus 2 pi over 3 to the 4th. That's right. 4 factorial is 4 times 3, which is 12, times 2, which is 24, divided by, so negative 1/2, sorry about that, negative 1/2 divided by 24 really should have been negative 1 over 48, not 24. Right, because it was negative 1/2 divided by 24, so that's negative 1 over 48. So this is my, right here, this is my answer for problem number 6. Does that make sense? It's a pretty procedural, thing that we're doing here. The thing that kind of stinks is when we have a complicated function for f, finding the derivatives, especially, so I'm doing this without using a calculator, right? But if you did have a calculator, you could find the derivative of the function evaluated at 2 pi over 3, and then take the derivative of your, of that, whatever the derivative is, evaluated at 2 pi over 3, and keep doing that. So if you had a calculator, that might be easier to do, but I'm doing it all by hand. Oftentimes, the Taylor series problem, and again, this year is all new, right? But typically, this was problem number 6. If you go back to the past, I don't know, dozen years or so of the AP exam for the free response question, usually problem number 6 was one dealing with the Maclaurin series or a Taylor series. And so those are the problems without a calculator. So that's why I'm doing everything like this without a calculator, okay? So that's how we do that. Lizzie, do you still want to see problem number 9?
I think after seeing this example, I'll be good because it's pretty procedural, so I think I'll be okay. Thank you, though.
Okay, cool. All right. So that's what we got going on for, the nth degree Taylor polynomials. And yeah, like I said, don't forget what you're doing here. So this right here, if I were to just look at up until this point right here, this is exactly what we would have gotten for linear approximations, right? That is your f of a plus f prime of a times quantity x minus a. This is what I said was L of x back when we learned linear approximations. But now we're saying forget linear, let's get a polynomial of whatever degree we want. This happens to be a polynomial up to degree 4. So this is the best polynomial to fit the function cosine of x centered at 2 pi over 3, right? I don't want to spend too much time, but if you think it would be valuable, do you want me to graph cosine of x, focus it, or center it about 2 pi over 3, and then put this 4th degree Taylor polynomial, or do you Do you see what, you know what I'll do? I'll give you a basic thing of what it's going to look like, right? So this is, oh, I don't want that guy. This is my basic cosine of x guy. And at 2 pi over 3, I'm going to be about right here, right? So 2 pi over 3, right? And basically what I'm saying is, so let me get rid of this red. Now I don't want to necessarily talk about, let's just say that would be linearization. Okay, now if I were to go to, let's say a, you know, the fourth degree Taylor polynomial that best fits this, it probably would look like this. It's definitely going to be equal to the function at 2 pi over 3. And then it's going to go something like that, and it's going to really like mold nicely to the function about 2 pi over 3. So definitely it's exactly equal to, so the green polynomial of degree 4, so that's quartic, is exactly equal to the original function, which is cosine of x at 2 pi over 3. And then it molds to the function as we go out from there, closer and closer. It's molding to, you know, to the function. Let me see. I actually lied to you. It's not going to look like this. And I'll tell you how I know. It's not going to look exactly like this. Watch this. Here's what it's going to look like. It's going to look like that. How do I know that?
First term's negative and it's an even degree.
That's right. So looking at the end behavior, right? So what I have here is the term that is of degree 4 has a negative coefficient. So remember, degree 4 is an even degree, so it either goes up and up or down and down, right? Well, because this is negative, I know it goes down and down. So it's got to go like that. And then I know that it's going to mold nicely to this function. So it's going to look something like this. So as I go away from where it's centered, which is 2 pi over 3, it's going to mold nicely to the original function, but at some point it's going to vary. So really this guy might look, you know, might be a little bit better. Who knows? Where it molds a little bit nicer to the function. I'm not doing a good job here. I thought this would allow me to. Anyway, so that's going to mold nicely to the function for a decent distance away from where it's centered, but we don't really know. Again, you know, they said interval of convergence, radius of convergence is not really going to be on this, so I'm just going to leave it like that. All right. All right, cool. Next, we're going to dive into the new stuff. Which is geometric series. So here we go. This is kind of what we have for geometric series. And, you know, these are all the things that we're going to learn today. But I'm going to make it so it's not going to be too much. It's going to be definitely you know, doable. You'll be able to handle it. So a geometric series is one of the only series where we actually can find what it goes to, what the sum is. For most other series, infinite series that we learn in calculus, it's only, hey, does this converge or does it diverge? And that's really it. But for the geometric series, not only can we determine whether it converges or diverges, but we can determine what it converges to. This is for an infinite geometric series. And again, you've already learned this in your other math classes. So this kind of gives you a good little bit about what a geometric series is. It looks like this, but again, that index, which this one up here has that n starts at 0, it doesn't have to start at 0. It could start at 15 or -3 or whatever. But this is what it looks like, right? Some constant times r to the n power. It could be to the n plus 1 or n minus 1 or something like that. But that's what it's going to look like. And really, the way that I look at it is, so let me write it down. So for geometric series, actually for infinite geometric series, if the common ratio is in between -1 and 1, so oftentimes you'll see that as the opposite value of r is less than 1. That just means r is in between -1 and 1. Then the series will converge and is equal to, and it's always the first term divided by 1 minus the common ratio. Okay, so they have different ways of saying it. Rogalski does not have first term divided by 1 minus the common ratio. But this is the way that I teach it because it's always true. This is always true. He goes through, well, if the first term is right, he has c divided by 1 minus r. C times r to the m over 1. Forget about all that stuff. It's always just whatever the first term is. No matter whatever that index starts at, you plug that in, you get your first term. That's your numerator, divided by 1 minus whatever the common ratio is. Okay, and that's what we're gonna use. So there are some examples in Rogalski's book. Let's pull those up. Here we go. This is example 3. So from Rogalski, and this is section 10.2. So this is from section 10.2, and it's example number 3. Okay, so for this, I would not leave it like this. A lot of times for geometric series, you're gonna have to manipulate the series so that it looks how you want it to look. And when I say how we want it to look, we want it to be something, some constant times some value raised to the n power or n plus 1 or something like that. And that is raised to the n power is our common ratio. So for something like this one, that's not raised to the n power, it's raised to the negative n power. So what I would say is this is equal to the summation as n goes from 0 to infinity of 5 to the negative first power to the n power. Okay, this is better. And all I'm doing is I'm saying that, 5 to the negative n is 5 to the negative 1 to the n. And now this is just equal to the summation as n goes from 0 to infinity of 1/5 to the n power. Here we go. This gives me something that is nice. I now look at this as whatever's inside here. That didn't work. Oh, come on, don't freeze on me now, buddy. Okay, there we go. It unfroze. Okay, so this 1/5 is my common ratio. Okay, so what I'm going to say is, because the common ratio is in between -1 and 1, it's 1/5. I know that this series will converge. Okay, and I know that it converges to, so this guy converges, and it converges to, so help me out, the first term. So here, when I say first term, whatever this index starts at, in this case, it starts at 0. You plug 0 in for n, and that's going to be the first term. What's 1/5 to the 0th power? 1, divided by 1 minus the common ratio. Well, the common ratio is 1/5. So this goes to 1 over 1 minus 1/5, also known as 1 over 4/5, which is just 5/4. So it converges to 5/4. Does that make sense? All right, I'm going to go to the next example. Here, I'll get the whole thing. Here we go. Okay, this is example 4. The next example. So me asks, when it says evaluate, we find where it converges to. Yeah, that's only going to be true for geometric series. The other series that we're going to talk about after this, it won't ask us to evaluate like what the series goes to or evaluate the series. It won't ask that. That's only for geometric series. So yes. Okay, so for this next one, now this is given to me in a nice way because I already have this common ratio that is inside. Man, this does not like the highlighter, I guess. I don't know if it's freezing on your end or if it's just mine, but I'm not going to use a highlighter anymore because there we go. Okay. All right. There it is. Okay. So this is my common ratio. So really, I know that this thing will converge. So this converges because the common ratio is in between -1 and 1. And it converges to, okay, so now I have to plug in my first value that the index starts at. So in this case, the index starts at 3, right? Up here, the index started at 0. Now this is 3. So I plug in 3 in for n, and I get that the first term is 7 times -3/4 to the 3rd power. So this is really going to be 7 times -3 cubed is -27 over 64. 4 cubed is 64, right? So this is just going to be, gosh, what is that? -8 with a 2, 16. What am I doing? 7 times -27. For some reason, I had a 4 in my mind. So that's 49, 9 with the 4. So that's going to be 14, 18. So -189 over 64. Right? Is that what you guys got for the first term? -189 over 64. Okay. So it converges to -189 over 64 divided by 1 minus -3/4. Okay, which is just -189 over 64 divided by, right, minus the negative, so it's 1 plus 3/4, so it's 7/4 which ends up being negative 189 over 64 times 4 over 7. Well, 4 goes into that once and into that 16 times. So this ends up being negative 189 divided by whatever that is. What? 2, 4, so 11, 112. Does that make sense? Is that what you guys got? Now, does that simplify it all? Yeah, so negative 27 over 16. Cool. All right. Next, example 5 from the book, and then we're going to move on from this. But this is a this is another example of what you might see. So evaluate this. First of all, determine whether it converges or not, and then, work it out. Okay, so the first thing I would do is apply the denominator to each term in the numerator. So I would say the summation as n goes from 0 to infinity of, so that's going to be 2 over 5 to the n plus 3 to the n over 5 to the n. Well, now I would call this the summation as n goes from 0 to infinity of 2 times 1/5 to the n plus the summation as n goes from 0 to infinity of 3/5 to the n. So that's a times right there. Okay. So what I'm doing here is, what I'm saying is this right here, this 2 is just going to be a coefficient of the term. That's a constant multiple, right, out here. And the 5 to the n in the denominator is the same as 1 over 5 to the n, which is 1 to the n over 5 to the n, or 1/5 to the n. And then over here, I have 3 to the n over 5 to the n, which is just the same as 3/5 to the n. So now you guys go ahead and see what that goes to, and then see what that goes to, and then you add them up to get your answer. I'm going to pause the recording so you guys can work on that. I'll give you 2 or 3 minutes. All right, so who wants to unmute and tell me what you got for the first? Treat these as 2 separate guys. What did you get for the first one right here? You can raise your hand or just unmute and do it.
5/4.
5/4? Did everybody get 5/4 for the first guy? And then what about the second one? What'd you guys get?
I got 5/2 also.
5/2? Sweet.
Yeah.
So then getting a common denominator, I'd say times 2 times 2. And so that's going to be what, 15/4? Is that what you guys got? All right.
I think the first one's also 5/2. That's what Kayla was saying.
Oh, 5/2 for the first one, not 5/4.
Yeah, 5/2.
Because did you forget to multiply by the 2?
Yeah.
Yeah, so that would be, okay, so then let's do this. 5 halves plus 5 halves, right? 5 halves for the second one also. Is that what you guys were saying? So 5 halves plus 5 halves is 10 halves. Or 5. Cool. All right. There we go. So that's geometric series. Again, you've seen this stuff before, just kind of reviewing. So let's 5 halves for the first one. Let's just do it real quick. Check this out. For the first one, what we're doing is the first term, when we plug 0 in for n, I get 2 times 1/5 to the 0th power, which is 2, over 1 minus the common ratio, which is 1/5. Plus, over here, I plug 0 in for n, and I get 1 over 1 minus the common ratio, which is 3/5. So this ends up being 2 over 4/5 plus, and this is 1 over 2/5. So this is 2 over 4/5 is the same as, so for that guy, it's 2 times 5/4, which is 5 halves plus 5 halves, which is 5. Okay, cool. All right, so that is geometric series, and now we're going to go on to, I'm going to give you some notes on the other series. Where am I? Okay, so geometric series done. So now we have harmonic series and P series. Okay, so here we go. Can I move this? That's good. Okay. So here we go. This is the definition of, a P series. It says, so, okay, what I have up here for under 3, this is from that series test worksheet that is on my website. But basically what we have is, if we have something like, the summation as n goes from, I don't care, 1 to infinity of 3 over n squared or something like that.